And here we go. Ladies and gentlemen, class recording has started. So, one thing, it's kind of related to class, but not really. Yesterday I was writing in my physical science class, and the little tip of my my marker came off. It still works, cause but I just don't know where the little white tip is on the. So if you see it like laying around, it looks just like a little cone, but I have no idea where it is. So anyway, if you see it, say, hey, there it is. No, I can still use it, but it's a little awkward. But so. All right. I was actually going to go see Mr. Horowitz. I was going to go and borrow his. So. But anyway, all right. Over the past couple of days, we've been working on the impulse-momentum equation, right? And we talked about the relationship between impulse and momentum. And yesterday, well, first, just to review that, right? So for your lab, it says impulse-momentum equation relates impulse and the change in momentum, right? And this equation right here is a more detailed version of the impulse-momentum equation, right? Because impulse requires force over a certain period of time. Change in momentum, you have the mass of the object, you multiply it by its change in velocity, because usually you're not going to change the momentum of something by changing its mass, because then it's a different object. But in your lab that we did last week, you were investigating this, right? And if you look on the very last page, your first analysis question was, did you verify the impulse-momentum equation, or something like that, some wording like that. Let me see what it says exactly. Does your data support the impulse-momentum theorem? All right? So in order to do that, we have to measure force, and we have to measure time, and we have to measure the change in velocity of the object and the mass. And so, pardon me for my low-tech graphics. I really thought I had a better picture of these than what I'm going to show you, but you saw some graphs that looked a lot like this in your lab, right? They're much better than this, but anyway. So here, right? Velocity graph on the top, force graph on the bottom. And we talked about the idea that your velocity graph, right, it started at 0, it dropped down, it was fairly constant for a while, then there was this big spike up, and then it went fairly constant again. Yes? Okay. And then the force graph, right, was 0, 0, 0, 0, 0, big spike, back to 0, 0, 0, 0. Right? And that's what we looked at over the past couple during your lab. Okay? And because your lab quest takes data at the same time, right? It takes multiple measurements at the same time. If we use this pink line to sort of relate some things for us, right? Let's go here to begin with. Okay? So, on the force graph, this is right when the force starts to increase. What supplied the force to the cart in your lab? The rubber band, right? But the rubber band, in order to supply a force, what does it have to do? It has to stretch, right? A rubber band is a good example of Hooke's law that we talked about in the last section, right? That the farther you stretch something, the more force it applies. The rubber band doesn't apply any force if it's not stretched from its original position, right? So while the cart is rolling along the track, before the string was straight, right, when it was loose, there was no force. And because of that, our velocity was real constant, right? The cart was just rolling along, right, in the negative direction. Then we start applying a force. When we start applying a force, what starts happening to the velocity? Well, what starts happening? During this section right here, from here to here, what's happening to the velocity? It's decreasing, right? If we look at this section right here, see how well I lined it up? Go a little bit more. Oh no. It's hard-headed. It's hard to do delicate things on the board. All right, so there, yes, velocity of the object is what? 0, right? And if we look at the force, what do we see about the force graph? Maximum value, right? Because that's when the rubber band is what? Well, when does the velocity hit 0? When the cart does what?
Can you remind us what we did again? I forgot what we had.
We had cart. You had the force sensor that was over on the one side.
Oh.
And we shot the cart down the ramp, and it's
We pushed it. Oh yeah.
yeah, we pushed it, and it bounced back to us,
Okay.
right?
Yeah.
Sorry. So then, right, as soon as it reaches that maximum value, or the maximum force value, which means the cart was as far away as it was going to be, then it starts coming back, and that's why the velocity starts going in the positive direction, because now it's coming back towards the motion detector, blah, 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 right? So, measuring our change in velocity, right, we said this was V final, this was V initial, we just subtracted them, that's how we got delta V, right? The impulse we did a couple of different ways, and there's a couple of ways that we can think about doing impulse. First, it's force times time, right? Impulse, we have talked about, is the force that's applied over the time during, or multiplied by the time over which that force is applied. But what do we see about the force this entire time? Is it a constant force? It is not a constant force. So it's kind of hard for us to multiply force times time because, well, what's the force? So there's two solutions to that problem. The first solution is the sort of, I don't want to say it's the lower level solution, but it's the one for people who don't have the math skills that sometimes are required. Okay? First thing that we did was we took an average of that force. Right? You did your statistics, you found the mean value, right? We took an average. And if everything came out right, the average value should have been here-ish, right? Half the time it's below the average, half the time it's above the average. So that's a good approximation of what the force would have been constantly over time. And I made that line a little bit too long, right? We should have gone like here to there, right? So all you did is you take the average, then you multiply it by the time over which that average occurred, and you can get the impulse that way. Okay? But we also introduced you to another method, and that was the integral. Okay? Way back when we were talking about motion graphs, we talk about finding the area under the graph. Does that sound familiar? Right? That we saw a velocity graph and we filled in the space between the x-axis and the graph itself with triangles and rectangles, and by finding that area of those triangles and rectangles we found the displacements. Okay? Sound familiar? I don't necessarily remember if you, I'm not necessarily, you know, hoping that you would be able to do that right now, but you at least remember we talked about it. Okay? A lot of times that area represents something. For example, on this graph, if we made a square that looked like this, actually I shouldn't do that, I should do this. I should actually make a shape. Right. So let's say we made that graph just like that, okay? Remember, these graphs represent something, right? It's x and y, but on this graph it represents two measurements. What do the x measurements represent on this bottom graph? What's on the x-axis on this graph? Time, right? It would be the width of this square, but really on this graph that represents a what? A time. And then the y-axis on this graph represents what? Force. So if we find the area of this square, length times width, right? Or whatever you call this, height times whatever, right? Multiply the two sides. On this graph, that would represent force times time. Yes? And what is force times time? Impulse. So if we find the area of this square, if that square was representative of the force that was occurring during that time, we could find the impulse by finding the area. Great, except finding the area of this space isn't very easy, right? It's not a regular shape. So finding the area of that becomes a little more difficult. It's parabolic in shape. What we get to is we could, if we wanted to, let's say I draw this line. Okay? Yeah, let me draw it in lighter blue so I can fill in the space. All right. Let's say I draw the line. Oh, not that. Let me do this.
I don't know, you did that before.
You probably did. Do you know what it's called?
I remember.
Okay.
It's been a while.
It's fine.
Last year.
So let's say that I draw this line like that. Here, let me zoom in so you guys can see it. It's going to take a little. All right. So that little light blue line that I drew in there, yes? Okay. That's actually a very skinny rectangle. Okay. It's got height, but it also has a little bit of width. Okay. And the area of that little skinny rectangle would represent the impulse during that very short time interval, because the skinniness represents a very short time interval, yes? Okay. And then what I could do is I could fill in another very skinny rectangle this way, right? And then I could fill in another skinny rectangle this way, okay? Each one of those very skinny rectangles has an area. But by making them very skinny, I can contour to the shape of this graph. I could contour to the shape of this graph better than by drawing just like one rectangle. Does that make sense? If I then added up all of the areas of all of these skinny rectangles, I would have the area of that shape. Does that make sense? As a better approximation than just like, well, I could do this if I wanted to. It is the area under the curve. Yeah, that's what I'm trying to get to. Like I could do this if I wanted to be, you know, kind of approximation. I could just draw a rectangle like this. I could just draw a rectangle like that and be like, okay, it's a little bit bigger, or maybe I divide by 2, right? But it's kind of what I'm looking for. By adding all of these little rectangles together, I get a much better approximation. Evan, go ahead. Again, you could, yeah, we could do that too, right? We could make something like, you know, a triangle like that, but again, that's not quite representative. It's an approximation, but it's not quite a representative picture. So that's kind of what we do at the introductory level. It's like, okay, well, this is close enough, right? But there comes time when we need something a little bit more accurate than that, right? And so these little, painstakingly adding up the area of all these little rectangles, that would take a long time, right? So we have a mathematical function that does that for us, right? Those of you that are in calculus, I don't think you've gotten there yet, but does that symbol look familiar? Anybody? That's okay. Yeah, this is probably after winter break. You spend the first half of the year talking about derivatives. Oh, are you guys there yet? Okay. So what it does, this is referred to as an integral function, okay? What it does is basically this. It takes these small little rectangles and adds them up. But what it actually does is does it better than we can, because these rectangles have to have a certain width for us to multiply the length times the height, or the width times the height, right? The integral function takes these rectangles and basically makes them infinitesimally small, right? And then it can fit every nook and cranny that is in there. So what it ultimately ends up doing is finds the area between the x-axis and that graph, which you saw on the lab quest when you did the integral. What did the lab quest do for you? Do you remember? It did, yeah, it did do all of it did all of those calculations for us. But if you remember physically, here, let me do this. It fills in the space, right? All it does is it just fills in that space with a solid color because that's what it's doing. It's finding the area of that space, right? So we'll see that there are times that we come across these different functions that we need to know this area because it represents something. It physically represents, in this case, the impulse. But finding that area on a graph that isn't straight is difficult. Just we can make approximations. We can kind of like say, oh, this kind of fits here, this kind of fits there. But really, when we get into the integral function, that's when we actually get that whole area filled in. So derivatives, for those of you that are taking calculus, derivatives find slopes, integrals find areas. Because mathematical functions model physical systems. That's what they do, or that's what physics is about, is finding the mathematical model to represent the physical system. And sometimes that means we have to find the area of an irregular shape, and that's where integrals come in. Okay? So that's what that integral function was doing for you in your lab. Cindy, go ahead.
No matter how small you saw the vegetables, will there still be a
Yes, but the integral value makes it. What the integral value does, it makes the rectangles infinitesimally small.
But they will still
No,
be
not if the width of this rectangle is essentially 0. Does that make sense? It can't be 0 because. So I get what you're saying.
Right?
Yeah, you're saying that even if even if I make these right. Right. But what the integral does is that it takes that into consideration and basically makes the rectangles so skinny that there is no space. Yeah, like how wide or skinny we make those rectangles would make a difference in how close we get. The integral takes that into account and gets rid of that problem. Right? Does that make sense? So, going back to your lab, if you look at the page where you did your calculations, right, it asks you to do the average impulse of taking the average force, multiplying it by the time interval. Oh, you guys can't see that. On your calculations page, which is page 3, it asks you to find average impulse here and average impulse here. What should you see about those two columns? They should be the same, because we're in essence calculating the same thing, just two different ways. All right? What should you see about this column versus that column? Average momentum change versus average impulse. Should be the same, because that's what impulse momentum theorem tells us, right? That close is good. I mean, like we're not going to be exactly the same, right? Because we're dealing with measurements, we're dealing with some of those uncertainties, blah blah blah, all that stuff, right? Close is good. Okay? The other thing it asks you to look at is to look at like trial 1 and trial 3, where you used 1 rubber band versus 2 rubber bands. Okay? Actually, if you look at it in this calculations table, I think my pen is running out of battery.
Oh,
So, not really sure where all my batteries went. Oh well.
oh, there's the rechargeable one.
See, this fixes it. So, if you look at child 1 versus child 3, where you went from 1 rubber band to 2 rubber bands, okay? If you did the way that you were supposed to, you should see momentum change be similar to one another. In both cases, you started with the same velocity, same cart, right? So, trial 1, trial 3, momentum change should be the same. But based on our discussion from yesterday, two rubber bands, what should you see about the force?
Different.
Doubles, or it's greater, right? But then the time interval does what? Time interval should do what?
Inversely.
It should get shorter, right? That inverse relationship, because in trial 1 and trial 3, you had the same cart doing the same thing. It went and came back, all right? So those are the kind of things that it's asking you to analyze in the analysis questions that are on the back page, okay? Good there? Ben, go ahead.
I have a question on like.
Sure.
I'd like to use this like bio.
Okay. What does the impulse momentum theorem tell us or explain for us? Impulse changes the momentum of an object, right? So if we go to the data table that's at the bottom of page 3, what should you see about, goodness gracious, what should you see about this column here and that column there? What is this column? Change of momentum. What is this column? So what should we see about those two things? They should be the same, because impulse causes a change in momentum, right? And that also holds true for the last column too, because this is impulse as well, just impulse calculated a different way, right? So these three columns all should be close, right? They might not be exactly the same, but they should all be close. Okay? And then, so that being the case, does our data support the impulse momentum theorem? Right. Does that make sense? Okay. What else? Anything else? Good there? Okay. If you want, if you're done with that, if you answer the questions, go ahead and turn it in. You can get it off your hands, that's fine, right? And then pull out the packet that I gave you this morning on conservation of momentum.
Can I ask you a question?
Sure.
Oh wait, no, I figured it out. You just
Okay.
answered it. I'll give you the one. Who's my question again, Anna? I'm not confident.
It sounds like a personal choice everybody needs to make, whether you should wear a bandana every day. I can't really tell you what the right answer is for that one.
There's not many negatives.
Except you'd be wearing a bandana every day. All right. So let's take a look at this demonstration. Okay. The next section of this unit deals with conservation of momentum. And if you've been paying attention for the past couple months, you probably could tell me, what we're going to discuss, right? The idea of conservation is one that keeps coming up over and over again, right? When we talk about something being conserved, what does that mean? Let's not limit ourselves to energy, right? If we talk about conservation, what does that mean? Something's not being lost or gained. So if we measure it, what do we end up with? Should be the same, right? So the one demonstration that we use to illustrate or to introduce this concept is usually this one, all right? So, two carts. I bring them together. Oh, I really thought I got one that didn't have the button, but oh well. So, yeah. All right, so red cart, it's got the little spring in it, yes, okay. I put it against the blue cart. Is that better?
Wait, am I blocking people? Is that better?
I want to make sure people don't miss
Like,
this.
I have like such a good view right now. It's not funny. Well, I can hold it. I can hold it. Like, I have the perfect. Oh, it's not
The
that.
cord's not long enough, so let me try this.
Hi. 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 Never mind. Not this way. Put it on where I
Well, here, I'll do this.
You know, should do like tilt the board. Tilt the board so it's like that way.
This demonstration is going to last like 1.5 seconds, just so you know. We've spent almost 10 times the amount of time that this demonstration is actually going to last on the camera thing. So, yeah. All right. So, a lot of times we start this discussion of conservation momentum with this demonstration. All right. Red and blue. Ready? Okay. I mean, you can watch up here too.
I know.
Live, that's true. Live action. Closed. There's a difference between closed circuit TV and live action. So, all right, ready? Here we go. All right. So the question comes up: is momentum conserved in that demonstration? Other than the fact that you guys can see it on your sheet, do we know why, or? All right. So the answer is momentum conserved in that demonstration? Here we have another representation of that demonstration. Have we looked at these two girls on the rollerblades yet? Yeah. Usually I use this when we talk about Newton's third law, right? Okay. So, same situation, both girls at rest. One girl pushes on the other girl, they both start moving. Is momentum conserved? And the answer to that question is what?
Yeah.
Yes, right? Did you want to? Okay. That's true. Let's take it out. That's why, or that's one of the contributing factors, right? Let's talk about it from the standpoint of momentum conservation. Evan, go ahead.
Is it because, like, they both slow? Isn't the conservation momentum that whenever you start with the
Yes.
They start with 0 and they push each other to 0.
But they're both moving now, right?
Yeah. But like they're going in opposite directions.
Right. That's the important part, right? Momentum being a vector quantity, right? The initial momentum of these two girls combined is 0. And the initial momentum of the two carts combined is 0. Because neither one of them was moving before the demonstration. They both end up moving after the demonstration, but we've made a big point of that momentum is a vector quantity. And that means that when they start moving, one's going to have a positive velocity, one's going to have a negative velocity. One will have positive momentum, one will have negative momentum. If both objects have the same mass, what should we see about the two velocities? It's got to be the same, right? And that means that when we add those two together, because conservation requires that we look at the total amount, right? The total amount of momentum beginning, the total amount end. Each one of these two individual objects has momentum, but because one is positive and one is negative, the total ends up being 0, right? So, if we do this, all right, so, right, big heavy mass. I'll fix it. All right, so big heavy mass added to one of the objects. Okay. So I put the big heavy mass on the red one. Right. We do the demonstration again. Yeah, blue one got annihilated. All right.
That's why if you're like
same situation, but did we see the two objects move the same? No, because it's not velocity that's conserved, it's momentum that is conserved. If red is heavier, if it has a greater mass, it has to have a smaller velocity to have the same momentum, right? But we still have that conservation of momentum, right? In order for us to see conservation of momentum, we require 0 total force, 0 net force. But we have to, it comes with sort of like a condition. And that condition being, we have to look at the difference between external forces and internal forces. All right? Internal force. Internal force we've introduced earlier, and as you can see here, all right? Internal forces are the. By the way, this happens on my monitor too, so it's not the projector. I do. I have a whole drawer over
Why
here.
does everyone ask me to do this laugh?
Anyway, so internal forces are Newton's third law, and we referred to them earlier as action-reaction forces, right? Conservation of momentum requires an interaction between two objects. If we're going to change the momentum of one thing, it has to interact with another object in order to change its momentum, right? Forces and all that stuff, okay? So the forces that they apply on each other don't change the total momentum because it changes the momentum of each one individually. Does that make sense? Red pushes on blue and changes its momentum, but what has to happen? Blue pushes back on red and does what to red? Pushes it, but from a momentum standpoint, gives it momentum. Actually gives it what? Impulse, which changes its momentum, right? But if we have an external force, like friction, right, then we might see a change in the momentum because friction can affect one thing without affecting the other thing. Does that make sense? Okay. So, on Monday, you guys will start looking at this idea of conservation momentum in a lab setting, and we'll do some application stuff probably on Tuesday. I don't think the lab's going to take you guys both days to do, so we'll start it on Monday, finish it up on Tuesday, and we'll start looking at some applications of conservation of momentum. All right? Have a good weekend, everybody. Oh, by the way, I think I told you guys yesterday, I did grade your test corrections. They are in there. They're back over on the side over there. So.
Can I get to do test corrections?
You can, yeah.